Method of transistor biasing. In the transistor amplifier circuit, so far as the biasing was done with the lead of the battery VBB, which was separated from the actual battery VCC used in output circuit, that is collector to base circuit. However, in the interest of simplicity and economy, it is desirable that transistor circuit should have a single source of supply. The one in the output circuit should be used in the input circuit. The following are commonly used method for obtaining the transistor biasing with one source of supply. Biasing resistor method, emitter bias method, biasing with the collector feedback method, and voltage divider method. Biasing resistor method. In this method, the resistor Rb is connected between the base and positive end of the NPN transistor. As you can see here, Rb is connected with the positive supply and base of the NPN transistor. Where the required zero signal base current is provided by the VC and it flows through the RB. It is because now the base is positive with respect to the emitter, base emitter junction is forward bias. The required value of zero signal base current, that is IB, can be made flow by selecting the proper value of RB. Let collector current IC to be zero signal. Let find the collector current IC to be for the zero signal collector current. Now what we know is the base current IB equal to collector current divided by the amplification factor beta. Applying Kirchhoff voltage law at the input side, that is base to emitter side of the circuit from A, B to N. Now you can see over here the total source is VCC. Voltage drop across RB is IB into RB plus voltage drop across the base to emitter diode VBE. That result, the RB is equal to VCC minus VBE divided by IB. If VCC is much larger than VBE, as we know that VBE has value of 0.5 volt for germanium and 0.7 volt for silicon, if we keep VCC 10 volt, then 0.5 volt is having very much less value. Automatically, it can be neglected. Therefore, RB is equal to VCC divided by IB. Stability factor. As the VCC and IB are known, VBE or any transistor manual, whether it is silicon or whether it is germanium, the RB can be readily found. It may be noted that VCC is a fixed known value quantity and IB is chosen at the some suitable value. Hence, the RB always remain constant or found directly. For this reason, this method is called fixed biased method. Stability factor. As we know, the stability factor has an equation S equal to beta plus 1 divided by 1 minus of beta change in IB with respect to IC. As we have seen that IB is independent of IC in above equation. That means this change is equal to 0. If this term is equal to 0, the S equal to beta plus 1. That means stability doesn't depend upon the IB value, it depends upon the beta value. In fixed bias method, IB is independent of IC. Thus, stability factor is a fixed in the fixed bias method is beta plus 1. It means that IC change beta plus 1 times as much as any change in leakage current. whole stability is now depend upon the beta. Since beta has a very large value, 100, 500, due to the large value of beta, the value of S in the fixed bias has give a poor stability. It has a poor thermal stability. Advantage. This biasing circuit is very simple as only one transistor RB is required. Biasing condition can easily be set and calculation are simple. There is no loading of source by biasing circuit since no resistance is employed across the bias-emitter junction. Disadvantage. This method provides poor stability. It is because there is no means of stop self-increasing collector current due to the temperature rise and individual variation. Since beta depend upon the temperature and individual variation, that means we can if we replace the transistor, the beta value varies, the stability get varies. Stability factor is very high. Therefore, there are strong chance of thermal runaway. Due to the disadvantage of this method of biasing, it is rarely employed. We will see an example of this. The figure shows the base biasing circuit. We have to determine the collector current IC, and if we change RB to 50K, what will be the operating point? Now, applying the Kirchhoff voltage law at the input side as we have done before. VBB is equal to IB, that is current flowing to the circuit, IB RB plus VBE, base to emitter voltage. Now neglecting base to emitter voltage, we will have VBB equal to IB RB, that is IB equal to VBB divided by RB. Now we know that VBB is 2 volt, RB is 100 kilo ohm. That means IB equal to 20 amperes, 20 microamperes. If IB current is 20 microamperes and is multiplied by the beta value, since beta value is given in the equation question as a beta equal to 50, then we can find the collector current IC equal to 50 into 20 microampere, that is 1000 microampere. That means it is 1 milliamp. Now, applying the Kirchhoff voltage law at the output side. Now, here VCC is equal to IC RC, that is voltage drop across the resistor RC, plus voltage drop across the collector to emitter junction of the transistor, this VCE. Now we know that if VCC is 9 volt, IC is 1 milliamp from the above equation, RC is 2 kilo ohm, we can easily find VCE equal to 9 minus 2, that is 7 volt. Now, the second part of the question is that if we change the RB to the 50K, we have to find a new operating point for the equation. Now, if we change the value of RB to 50K, IB equal to VBB divided by RB, that is 2 divided by 50K, that is equal to double of 20 to 40. As you can see, you drop the beta value from 100 to 50, your base current increase double, that is 20 to 40. Now, if we multiply the collector current again, you will see it will increase twice, 1 milliamp to 2 milliamp. And as a result, we will get VCE as a 5 volt. Emitter bias method. Now, in this method, wait a second. This circuit differs from the base bias circuit in two important respects. First is it is used two separate DC voltage sources, one with the positive VCC and one with the negative VEE, as you can see from the circuit, VCC and minus of VEE. Normally, the two supply voltage will be equal. However, it may be different. Secondly, there is a resistance Re in an emitter circuit, which is new to us. Now, we will first see how can we analyze the circuit. Now, by applying the Kirchhoff voltage law at the input side of the circuit. VE is the total source is equal to current flowing through the IB, RB, voltage between the base emitter, that is VBE junction, and the current flowing through the emitter resistance IE, that is IE into RE. As we know that collector current is beta times of base current IB, and collector current is also equal to the emitter current. Now substituting the value of IB in above equation, we will get VEE is equal to IC divided by beta RB plus IE RE BE. If we can replace this collector current IC by the value of IE, we will have equation VEE minus VBE IE divided by beta RB plus IE RE. That means emitter current is equal to VEE minus VBE divided by RB divided by beta plus RE. That is emitter current, and which is approximately equal to the collector current. Applying the Kirchhoff voltage law at the output circuit. Here VCC is equal to VCC is equal to current flowing through the resistance RC, that is ICRC, voltage drop across the collector emitter junction, that is VCE, voltage drop across the resistance RE, that is IERE, and our minus power supply, that is minus of VEE. Therefore, VCC is equal to ICRC plus VEE plus VCE minus of VEE. Now, as we know that IC is nothing but IE, you can replace the equation of value of IE with respect to the IC. Now, the above equation is completely for the collector current, and we get collector emitter voltage VCE is equal to VCE plus VE minus of IC RC plus RE. Stability factor. Now we have a collector current from above equation, the IE equal to IC equal to whatever you can say, both are the same, having same value, as we know that the maximum emitter current flows to the collector. That is emitter current is equal to nearly equal to collector current. VCC, sorry, VEE minus VBE divided by beta times of RB, 1 by beta times of RB plus RE. Now, if we make this denominator terms somewhat different, that means if we make Re much larger than Rb divided by beta, we can neglect the term Rb divided by beta. If the beta gets cancelled, the equation will be collector current equal to VEE minus VBE divided by Re. Again, cross thinking, VBE has very less voltage, that is 0.7 or 0.3. That means VEE is much greater than VBE. If that the case, then IC is equal to VEE divided by RE. Now here what happened, that current doesn't depend upon the base to emitter voltage, and it doesn't depend upon the inherent property of the transistor beta factor. Ultimately, our stability factor will reduce to a good value. and we can have a good stability through this circuit. Now, for the question, we will solve one problem of based on this circuit. Now you can see example for the emitter bias circuit shown over in the figure. Find current emitter current IE, collector current IC, collector voltage Vc, Vce, and for the beta value of 85 and Vbe is given as a 0.7 volt. Now solution, as we know that collector current, which is nothing but the emitter current, equal to VE minus VBE divided by RE plus RB divided by beta. Now here we have a very simple equation. Since we know all this value, just like VE is minus 20, we can write 20 volt. VBE is 0.7 minus of 0.7, since equation has a minus sign. Here, some students get confused. We have to write minus 20. No, we don't have to write minus 20. We will write directly 20 volt. Now, RE is 10 kilo ohm plus RB 100K divided by beta factor 85, which result into current as a 1.73 milliamp. Now, collector current which he asked is up, over here. This is what we call as a collector current. So collector current, collector voltage is equal to VCC minus of voltage flowing through the resistance RC, that is IC RC, and it is equal to VCC is 20, IC is we have 1.73, and RC is given as a 4.7 kilo ohm, and therefore collector voltage is 11.9 volt. Similarly, the emitter voltage is known as at the emitter junction of the transistor, and in between these we have collector emitter voltage, that is VCE. This is nothing but VCE. Since VCE is the difference between the collector and emitter voltage, that means VCE is equal to VC minus VE. Therefore, we have to find VE. Now, this VE, which is this voltage at the emitter terminal of the transistor, VE is equal to minus of VEE plus of IERE, minus of VEE, or voltage drop across the emitter resistance, that is IERE. And since we have writing minus sign directly and the VEE, so we will write that 20 plus, as we know, emitter current is nothing but the collector current, which is 1.73 milliamp. We have find it out, multiplied by the resistance value, that is 10 kilo ohm, and VE is resulted as a minus of 2.7 volt. As we have discussed, VCE is nothing but VC minus VE, that is 11.9 minus of 2.7 volt, minus get plus, and 11.9 plus 2.7 result into 14.6 volt. Note that the operating point now is VC equal to 14.6 volt and the collector current IC is 1.73 milliamp. I'm biasing with the collector feedback resistor. In this method, one end of RB is connected to the base and other end is connected to the collector, as you can see in the figure. Here the required zero signal base current is determined not by the VCC but the collector base voltage, that is VCB. It is clear that VCB forward bias collector base emitter junction. Hence, the base emitter current IB flows through the RB. This caused the zero signal collector current to flow in the circuit. Now we can analyze the circuit. As you can see, by applying the Kirchhoff voltage law, we will have VCC at the input side. VCC is the total source equal to IC into RC, IB into RB plus base to emitter voltage, that is VBE. Now, if we find the value of RB, which is equal to RB equal to VCC minus of ICRC minus of VBE divided by IB. Now, as we know that IC is nothing but beta times of IB. Therefore, further we substitute the value of IC in the equation and we will find the whole equation in terms of IB. Now, collector emitter voltage, that is VCE, is over here is base to emitter voltage VBE plus collector to base voltage VCB. Now, this is what we learned to be collector emitter voltage. And this is VCE. And this is our VBE, base to emitter voltage. VBE. Remaining collector to base voltage, that means from here collector to base voltage. You can easily identify that collector emitter voltage is nothing but collector base voltage from here to here plus base emitter voltage VBE. Collector base voltage is equal to VCE minus VBE. Now, RB, which is equal to, we will have as a VCB, that is over here, collector to base voltage VCB divided by the current flowing through the IB, VCB divided by IB. Now what we find, collector base voltage is nothing but collector emitter voltage minus VBE. Now equation of RB is, we will, if we equating the RB, we have two equation for RB. One is this and one is this. If we equate both of them, what we will get, IB get cancelled. Again, when we the remaining VBE get cancelled, what remains is IB get cancelled, VBE get cancelled, and the remaining part of the equation you can see as VCE equal to VCC minus of beta times of IBRC. Now, minus of beta time of IB is nothing but IC. We have shown it. Now that means VCC minus ICRC is equal to VCE. Hence, we know that IB into RB from this equation. IB into RB is equal to VCC minus beta times of IBRC minus of VBE. And we also know that the collector current is nothing but beta times of IB. That means base current is equal to collector current divided by beta times. So we substitute the value of IB in above equation. Collector current into RB divided by beta times equal to VCC minus ICRC minus of VBE. By this equation, we will have IC is equal to VCC minus VBE divided by RB divided by beta plus RC. Advantage. It is a simple method as it requires only the value of resistance RB. The circuit provides some stability of operating point. Disadvantage. The circuit does not provide a good stability because the stability factor is fairly high, you can see. So it is lesser than the fixed biased method. However, it is high. This circuit provides negative feedback which reduce the gain of the amplifier. So we cannot use this circuit for amplification. During the positive cycle of the signal, the collector current increase. The increase in collector current would result in a greater voltage drop across RC, and this will reduce the base current. Hence, automatically the base current get reduced. Stability factor, which is less than beta plus 1, which is the value of the fixed bias method, but still it is a sufficiently high stability factor. It shows sufficiently high stability factor. Suppose the temperature increases. If the temperature increases over here, increase the collector leakage current, hence the total collector current. But soon the collector current increases, the collector emitter voltage decreases due to the greater drop across the RC. The result is that the collector base voltage decreases and lesser the voltage is available for the base resistor, the base current will decrease. Automatically that decrease the collector current originally. We will see the problem for this. Figure shows a silicon transistor biased by the collector feedback method. Determine the operating points given that beta is 100 for the transistor. Now we have VCC as equal to 20 volt, RB as 100K, RC as a 1K. Since it is a silicon transistor, we know that VBE is 0.7 volt. Assuming that IB we obtain in milliamp using this relation that RB is equal to VCC minus VBE, VCC minus VBE minus of beta times of IBRC divided by IB. Now, if we don't know the value of IB, but we know all other values, so we can easily find the value of IB, which is nearly equal to actually 96 microampere. If we convert that 96 microampere in a milliampere, it is 0.096 milliamp. Now we have a beta equal to 100. If we multiply 100 to 0.096, we will have 9.6 milliamp. Now collector emitter voltage, that is VCE, collector emitter voltage VCE is equal to VCC minus ICRC. We have VCC is equal to 20 minus of 9.6 IC multiplied by RC. That is VCE equal to 10.4 volt. Operating voltage will be VCE equal to 10.4 volt and collector current, that is 9.6 milliamp. Voltage divider method. In voltage divider method, what we have? It is most widely used method for providing the biasing and stabilization of the transistor. In this method, two transistors, that is R1 and R2, are connected across the supply voltage VCC and provide the biasing. The emitter resistance RE provides stabilization, and the name voltage divider comes from the voltage divider network formed by the R1 and R2. Voltage drop across R2 Voltage drop across R2 is known as a V2, and it is the used to forward bias the in base emitter junction. This causes the base current and hence collector current to flow in zero signal condition. Suppose that the current flowing through the R1 is I1. The base current is very small. Therefore, assuming the reasonable accuracy that the current flowing through the R2 is also I1. If the total current flowing through this network is I1, then the total current I1 is equal to total source VCC divided by total resistance, that is R1 plus R2. Now, voltage that bias the base emitter junction is V2. Now, this voltage we have to find. That means V2 over will be here. V2 is equal to VBE, that is base to emitter voltage, plus emitter voltage VE. Now, emitter voltage is nothing but current, emitter current IE into RE. Now, collector current, which is nothing but the emitter current, is now is equal to V2 minus VBE divided by resistance RE. Now, if we apply voltage Kirchhoff voltage law at the output, VCC, which is over here, is equal to current for the resistance RC plus voltage drop between the collector to emitter voltage, that is VCE, plus the voltage drop across emitter resistance, that is IE into RE. VCC is equal to ICRC. Now we have emitter current we can replace by the collector current IC plus VCE. That result VCE is equal to VCC minus ICRC RC plus RE. Stability factor. Now, as we know the stability factor equation S equal to beta plus 1 divided by 1 minus of beta DIB divided by DIC. Thevenin theorem equivalent circuit for the voltage divider is, we have find this. Sorry, I have to say that this circuit, when we find the Thevenin equivalent of this circuit, it will result into this. That means the source V2, if they replace, I have said it is E0 and the resistance R0. Thevenin theorem says that any bilateral network, bilateral that is 2-point network, here we have these 2 points. One is over here, A, and B. Then they replace by a source E0 and a series resistance of R0. Over here you can see. Now, the Thevenin equivalent circuit for the voltage divider is shown in the figure. Now, for the total source is E0, which is equal to the current flowing through the emitter resistance IERE, current flowing through the base resistance, that is R0, IB R0, and base to emitter voltage, that is VBE. As we know that I is nothing but the base plus collector current. If we substitute that value in the equation, we get E0 is equal to IB plus IC RE plus IB R0 plus VBE. Now, differentiating above equation with respect to the collector current, we will get, since it's a constant value E0, it will be 0. Differentiation with the IB with respect to IC is DIB divided by DIC plus DIC divided by DIC is 1. RE DIB divided by DIC R0 and VBE equal to 0. Now rearranging the equation, we will get DIB divided by DIC is equal to minus of RE divided by RE plus R0. Now substituting the value of DIB divided by DIC in the stability factor, we have S equal to beta plus 1 divided by 1 minus of beta minus of RE divided by RE plus R0. Now, if we rearrange the equation, we will get S equal to beta plus 1 into 1 plus of R0 divided by RE divided by beta plus 1 plus R0 divided by RE. Now, this ratio of R0 RE, if it make more than 1, what will happen? Sorry, I'm sorry, I written it's wrong. It should be made less than 1, very much less than 1. It should be very much less than 1. Then above equation become 1 and नीचे यहाँ पर R0 by RE is nearly equal to, as you can say, we can neglect that since it is very much less than 1. So automatically S result into 1. Now we will see one problem based on the voltage divider biasing. Wait for a second. Now, in the example, you can see that the voltage divider method has been drawn for the figure 9.25. I will show you the figure 9.25. And we have to draw the DC load line and determine the operating point, means assuming the transistor is to be silicon. Now, first we have to see what is the, here is the circuit. 10K, R1 is 10K, R2 is 5K, RC is 1K, and RE is 2 kilo ohm, where VCC is 15 volt. Now for the DC line, we need two main point, that is maximum current IC and VCE. Now, collector emitter voltage VCE is given by VCE is equal to, as we know, VCE is the collector emitter voltage over here, which is equal to VCC minus IC plus RC, sorry, VCC is equal to voltage drop across RC, that is IC into RC, VCE or voltage drop across the resistance RE, that is IC, IE into RE. Now we find that VCE equal to VCC minus IC into RC plus RE. And also we have done over here. You can see over here VCE equal to VCC minus IC into IC minus IC RC plus RE, that we will use in this equation. Now, when IC equal to 0, that is VCE equal to VCC equal to 15 volt, we have obtained it is to be 15 volt. We can see in the figure circuit diagram they are given as a 15 volt. Please locate the first point B on the load line. Now VCE equal to 0, that means IC is equal to VCC minus VCC divided by RC plus RE, which is equal to 15 divided by 1 plus 2 ohm, that is 5 milliampere. Now let's locate the second point. For the second point we have to make IC equal to 0. As you can say, point B 15 volt is shown over here. The point A, we will take VBE is equal to 0.1 volt. Sorry. If we make IC equal to 0, VCC is nothing but 15 volt, and when we make a VCE equal to 0, IC is equal to 5 milliamp. We will get point A and B, the load line, and we will draw the load line. Now to find the operating point Q. Now, operating point for the silicons has to find when VBE equal to 0.7 volt, voltage across the resistance 5K. What is the voltage across the resistance 5K? We have considered over here. This is the potential across the I, that is V2, okay, which is nothing but if we calculate sorry, this is the circuit and this is the 5K. Now V2 is equal to VCC divided by 10K plus 5K. What is 10K and what is 5K? This R1 is 10K and R2 is 5K. Same circuit we have studied when we are doing the, you can see V2 is equal to VCC divided by R2 plus R1 plus R2 into R2. R2 is 5K for us, R1 is 10K for us, R2 is 5K for us. Now if we substitute that V2 value, that is 15 volt for VCC, 5K, that is R2 divided by R1 10K plus R2 5K, that is totally equal to 5 volt, that is V2 is equal to 5 volt. Now for emitter current IE, we have an equation. Emitter current IE V2 minus VBE divided by RE. Therefore, V2 is now we know 5 volt. We will substitute that value minus of 0.7 volt VBE divided by 2K is equal to 4.3 divided by 2K, that is 2.15 milliamp. Now this is emitter current, which is nothing but the collector current. As you can see, emitter current is equal to collector current. Collector emitter voltage VCE, as we know from the equation we have find VCE is equal to VCC minus ICRC plus RE. Now, if you can see VCE equal to VCC minus ICRC plus RE. These are all the known values for us now. If we substitute these values, the VCE will result into 8.55 volt. Now, collector current is 2.15 milliamp, whereas collector emitter voltage is 8.55 volt. This is the operating point for the load line over here. The figure shows the operating point on the load line, and coordinates are IC is equal to 2.15 milliamp and VCE equal to 8.55 volt. Bibliography, okay. Stability factor, we have already discussed. Bibliography for this material is the V.K. Mehta, Principle of Electronic. Thank you.